Welcome to Virtual Conference in Chemistry and its Application 2022. My abstract number is 67 and my title of the presentation work is Exploring Alkali Metal Cation Hydrogen Interaction in the Formation of Sandwich Complexes with Cycloalkanes. It is a DFT approach. This is my affiliation, Henry Girls College, Guwahati, India. My email ID is apun.ken@gmail.com. First of all, we will introduce the topic basically. What is that? The cation-alkane interaction. Although I have studied the cation-hydrogen interaction, in some literature it is mentioned that it is cation-alkane interaction. So I have written it here, cation-alkane interaction. The cation-alkane interaction is fairly strong. Such interaction plays major role in basically in CH activation reaction and cation passes through lipid bilayer. Cation-alkane interaction is predominantly stabilized by induction component. The dispersion component plays a nominal role in such interaction. Not much studies have been reported in cation-alkane interaction from the perspective of half sandwich and sandwich complexes. Sandwich and multilayer complexes of 1,3,5 trifluorocyclohexane and 1,2,3,4,5,6 hexafluorocyclohexane involving alkali metal ion are reported by our group. Among the cycloalkanes, such interaction is only reported with cyclohexane. This prompted us to explore such interaction in the formation of half sandwich and sandwich complexes. Although here I am reporting the half sandwich complexes, but some of our studies have revealed that some of the sandwich complexes are also stable or quite strong in terms of stability. What are the computational theoreticalities I have used? I have used M062X functional Minoseta density functional theory at 631G GDP basis set. And to validate the result, we have also made use of WB97XD and B3 LOB functional. Similarly, we have also validated the use of this other basis set like 631 single plus GDP and 6311 double plus GDP basis set. We have calculated the stability of the products in terms of stabilization energy, which is defined as the energy calculated of the complex and energy calculated of the monomers. Difference between them is known as stabilization energy. To get the positive stabilization energy, we have defined in this way in terms of negative. Higher the SE value, more positive the SE value, higher is the stability of the product. We have also made solvent phase calculation whether the products are stable in solvent phase or not. For that purpose, we have used polarization continuum model in which solvent is considered to be a continuum. NBO calculation is also performed to see which one is the donor, which one is the acceptor. Then multi-WFN software is used for topological analysis from which we can confirm whether the nature of interaction is covalent or non-covalent, and some idea about this electrostatic and electrostatic interaction also. Then whole study has been performed within Gaussian line program package. Now, what are the Sojan system? In terms of cyclo, we have made use of cyclo system and bicyclo system, like cyclopropane, cyclobutane, cyclopentane, cyclohexane, bicyclo 2,2,2 octane, then adamantane. And from alkali metals and lithium, sodium and potassium has been exclusively used. Although we have performed some studies with the alkaline earth metal ion, but the study is not completed till now, so we have reported here the formation of the complexes using lithium, sodium and potassium ion. Now here although I have written the geometry of the complexes, here is the distances between the metal ion and the hydrogen atom that is closest to the vicinity of the cycloalkane interaction has been reported here. Here is seen that lithium cyclopropane complexes, the bond distances or interacting distances varies within some range, very small. Potassium, sodium, potassium. Here we have said C-pro means cyclopropane, C-but means cyclobutane, C-pent means cyclopentane, C-hex means cyclohexane, C-bicyc means 2,2,2 bicyclooctane, and Ada means adamantane. Here are the bond distances. From this interaction and geometry, we can conclude that both eta 3, that means trihepto and tetrahepto mode of interaction is observed in case of these cyclocompounds. Stronger interaction is expected with the smaller metal ion, as the size of the distance between the hydrogen atom and the metal ion is lesser in case of smaller ions in all the complexes. However, not all M and H interaction are equally strong because the distance varies. Some of the hydrogen is contributing more, some of the hydrogen is contributing less. Now herein, eta 3 mode of interaction has been represented here. Here we have seen that these are eta 3. Herein we have now shown this lithium complexes as a representative case. That means eta 3 and this is eta 4. From the geometry we can conclude that eta 3 mode of interaction are observed with cyclopropane, cyclobutane, cyclohexane and adamantane, whereas eta 4 mode of interaction is observed in case of cyclopentane and bicyclooctane. Now we have calculated the gas phase stabilization energy to predict the stability of the complexes. Here it is seen that as we predicted from the bond distances or distance between the hydrogen atom and the metal ion, higher interaction energy is observed in case of smaller metal ion. Similarly, larger the alkane and higher is the interaction energy in most of the cases. From this we can say that complexes are moderately stable in gas phase with stabilization energy ranging from 3.03 to 26.55 kilocalorie per mole, and stability of the complexes increases with the increasing the size of alkane, and stability of the complex decreases with the increasing the size of the alkali metal ion. Now for we have want to study the feasibility of the interaction. For that purpose, we have calculated the enthalpy and free energy changes in the formation of the complexes, and it is found that enthalpy change for all the systems are negative. That means the formation of the complexes is exothermic in nature, and delta Z value except the complexes of potassium with cyclopropane, delta Z values are also negative. That means most of the complexes is spontaneous. Formation of the complexes is spontaneous in nature, except these potassium cyclopropane complexes. That is, formation of the complex is endothermic and spontaneous, and there exists an inverse dependence of delta H and delta Z value with the size of the metal atom. Here it is seen that like earlier stabilization energy, larger the size of the metal ion, less is the nothing. That means less negative is the delta H and delta Z values. Now we have made the solvent study. Herein we have shown with the help of bar diagram. Red colors are in positive stabilization energy and other colors are negative stabilization energy. Negative stabilization energy means the instability of the complexes. From it is seen that although gas phase complexes are stable, but the complexes in presence of solvent, we have taken 4 solvent dielectrics like cyclohexane, ethanol, DMSO and water. In all the 4 complexes, it is seen that the complexes are likely to be unstable, or that means from this we can conclude that solvent phase complexation is not favorable for such complexes. We have made use of other functional as I mentioned earlier during computational details. It is seen that the result produced with M0628 functional and WB97XG functional are quite comparable. The difference is only about a maximum of 0.53 kilocalorie per mole, and from that we can conclude that the method that we have used, or the functional that we have used, is reasonably a suitable choice. Moreover, whenever we are calculating the stabilization energy or any parameter from single point calculation, we also validated the result by using optimization by taking lithium complexes as representative case, and from that we have found that the result obtained from the optimization of with WB97XT functional or B311 functional are almost close to the result obtained from the single point calculation. So from this we can say that to scrutinize the role of the basis set and functional in terms of computational demand, single point calculation provides reasonably a good result. Next we have validated the basis set, validated the suitable basis set. It is said that although we have used the higher basis set like 6311 plus GDP, the interaction energy does not vary to a significant level. It varies up to 0.3, 0.5 kilocalorie per mole except 1 or 2 complexes. From this, it can be concluded that addition of extra diffuse basis set do not impart significant effect on determining the stabilization of the complexes. So by from the view of computational efficiency, the use of 61 double plus CTP function is reasonably a suitable one. We have also the we have made a homolumo perspective studies. From this it is seen that herein we have represented only the complexes of with the augmented as a representative case. It is seen that HOMO is mostly localized in the alkane, around the alkane. All the metal ions are almost free, whereas HOMO is, that means we can say that HOMO is alkane centric. However, if you look at the LUMO of the same, it is found that LUMO is the metal centric predominantly. So from this we can also predict that HOMO, the donor will be the predominantly the alkane will be the donor and acceptor will be the metal ion. Again, we also made calculate the HOMO energy and plotted the HOMO energy and stability of the complexes, and it is found that there exists a very strong linear relationship between the HOMO energy and the stabilization energy of the complexes. From this we can say that some electrostatic interaction may also be involved in the process. Then charge transfer versus stabilization energy. We have calculated the amount of charge transfer in the interaction and stability of the complexes and plotted against each other. Here also, like the HOMO energy and stabilization energy, it is found that a significant linear relationship between the charge transfer and stabilization energy. This also validates that although there may be nominal, but some electrostatic interaction is also present here. Now we try to predict whether non-covalent interaction is there or covalent interaction is there. For that purpose, we have also made topological analysis, and also this also validate the mode of coordination also. For this, we have shown this lithium complex and complex with the cyclopropane and adamantane as representative case. It is seen that cyclocomplex is eta 3, and this with adamantane it is eta 3 mode of interaction. As a representative case we are showing, and the values are also shown as a representative case. From these values it is shown that since these values are very small, so there is exclusively non-covalent interaction between them. For covalent interaction, these values will be highly large. So it is we can say that the interaction is largely covalent in nature. Now, to predict the donor, we also predicted the donor acceptor from the HOMO perspective. From NB analysis also we can validate the result, and for that purpose we have made the homologue analysis, natural bond analysis, orbital analysis. From that we can say that it is seen that here also lithium complexes and complexes with the cyclopropane and adamantane are shown as representative case. It is seen that the anti-bonding the bond donor is the CH bond, whereas the acceptor is the anti-bonding metal ion. And here we have written the second order perturbation energy. This is second order perturbation energy. From general concept, higher the second order perturbation energy, higher is the stability of the product. That means most stable interaction is given by the donor CH bond and the acceptor in the anti-bonding lithium. So in case of lithium, it will be lithium. So similarly for sodium complex, it is the donor CH bond sodium. For the potassium complex, CH bond and potassium. Another one more thing we can say, the CH bond is the predominant donor, and anti-bonding for lithium it is twice S, for sodium it is thrice S, for potassium it is 4S. Orbital of the metal ion acts as the acceptor. And E2 value also increases with the size of decrease in size of the metal ion. That means like stabilization energy, E2 value also validates that smaller the metal ion, higher the stability of the interaction. And there exists also a linear relationship between SC value and E2 values. That is second order perturbation energy. We have also made some effort to study the effect of complexation on CH tracing frequency. It is seen that this is of this free alkane, whereas this is in complexation. Here it is seen that the CH these are in CM inverse values. This is seen that there is red strip in the CM matrix CH tracing in complexation. and it is up to 170 centimeters. If you consider here we have recording this symmetric one, but in later one we can also discuss about this asymmetric one also. A significant shift is there for smaller ion, that means higher the stronger interaction. Stronger the interaction, higher is the redshift. Redshift means the lower frequencies. Now moving into the conclusion. The complexes are stable in gas phase, while the presence of solvent activities favor the process of complexation. The stability of the complex increases parallelly with the size of the alkane and thereby reducing the mobility of cations in liquid alkanes. The complexation is enthalpy and free energy driven. The interaction is non-covalent and somewhat charge controlled, although some further studies required to validate the concept result. Higher the charge transfer, higher is the stability of the complexes. The CH bond is the predominant donor side and antibody 2s, 3s, 4s orbitals are the acceptor orbitals for lithium, sodium and potassium respectively. Stronger the interaction, higher is the redshift in the symmetric CH staging frequencies. Nonetheless, experimental investigation are required to validate the stability of the complexes or validate our studies. Thank you. These are the references that lead to our study mostly, and other references are also there. Thank you.